thank you to IIIT Allahabad for making this possible, and thank you to the Pragma team for inviting me here. It's a pleasure talking about distributed systems and machine learning on top of that. So let's start. I'll just share my screen, guys. Do let me know. I think it will be visible. We did a demo before this, but yeah, it is visible. Awesome. Okay, so what we are going to do today is we are going to see how machine learning is done in large-scale distributed systems. What that means is that you don't have a single computer or you don't have a single database. You actually have multiple services, multiple databases spread across the earth pretty much. Okay, so let's say Google has data centers in India, has them in the US, in UK. And what they end up doing is that they need to run machine learning on top of these data centers and then aggregate results and make sense out of that data. Okay, so that is what we are going to try to do. But even before we start, even before I say what the agenda is, I want to give a quick, I want to get a quick understanding of what is machine learning. How many of you know what machine learning is? Can you hit the raise hand button below? Okay, one person, two. So there's a few people who know what machine learning is in general. All right, but I'll just give you a quick recap. So let's say I have a graph of housing prices. So area versus price. Now, the more area you have, you expect the house to have to be more expensive. But in this case, there are anomalies. There might be a place which is, let's say in the rural areas, the housing price is cheap. It's expensive in the city, so you bifurcate that way. But eventually you end up with a graph looking like this. Now, if you want to predict a house price for an area that is unknown, so if there's a new house, you built it of 3,000 square feet, you want to predict the price. One interesting way, one sensible way would be to draw a straight line through the graph and then plot the point using the x-axis onto the y-axis. Okay, simple thing called linear regression. If you use complicated models, then you can fit the curve better. But over here also there is an extreme thing that you might overfit the curve according to the input data instead of according to the generality. So these are some things about machine learning. Basically, we have a set of inputs and we want to predict an output given a new set, given a new input. Okay. So the general model is this. Usually in any machine learning system, we have a large number of inputs, which is a lot of data being pushed into a learner. Okay, this is your machine learning bit, that red box over there. That's the database. Over there, I mean, after this, you have the blue box, which is drawing inferences from this data. In fact, this is also part of machine learning. And finally, you have decisions. This is more like artificial intelligence. So machine learning would be taking all the images or the weather data in a car, and decisions would be turn left or turn right. Inferences would be something like, if the weather is snowy, chance of accident goes high, so decision, reduce speed. Okay, and how do you draw this inference? Well, you learned from all the input data being pushed into the self-driving car. General idea, this is what we're going to be focusing on. The database plus learner bit is what we are interested in, something that gives out inferences. End of the talk, that's a good thing. The general idea of machine learning is rather simple. Take a lot of inputs and try to predict outputs using that. So what we are going to do is we are going to figure out today, if you have data spread across different systems, how do you run machine learning on top of it? When you're going to do that, you're going to end up defining a schema, a certain rules, I mean, a set of rules or a format before you do the machine learning thing. So how is the data being prepared for ML, and what are the engineering challenges when you take a large distributed system and try to learn ML on top of it. So this is the agenda, and yeah, this is who I am. I think Aryan has done a great job, so I'll just skip this slide. Okay, now for the time being, let's assume that machine learning is easy. Okay. You take data, you run it through a neural network, and you get an output. Let's assume that part is easy, or you use a support vector machine or something. But what is the problem in the topic that we are talking about. The problem is that the data is distributed. Okay, it's distributed across services, which means that they have different tables. The data is in different schemas, and when you're persisting it, you're sending in them parallelly to different places. Okay, so how do you combine all this data is the real problem. So initially what used to happen, I don't know if you guys have, I mean, how many of you are experienced, but there used to be a lot of monolith architectures out there. Even now, there are many companies which work with monoliths. What happens there is that you have a lot of clients that you're seeing over here. You have mobiles, you have desktops. They're connected to, let's say, a food delivery service. It's a single service which is deployed, and you have a single database. Okay. What used to happen is we used to hire data analysts who would run SQL queries on that data. So someone would ask, how many people bought food from this restaurant? And a person would literally fire an SQL query. A person, for example, me, I used to, there were a few times when to build reports, you need numbers. Where are you going to get those numbers from? If you don't have a framework, if you don't have a well-set process, somebody has to do it. So that would be the engineers. Later on, data analysts would be specifically hired for just firing queries on top of this. And they would have indexes on copies of the table. They would create views, but these had quite a few issues. So the first one, I mean, if anyone in the comments can tell me what is an issue with this architecture, where you have people firing SQL queries on a production database. I'll just give you guys 2 minutes. You can, even if you don't come with the answer, just think over it, that what could be a serious issue. Okay, Manthan has one correct answer. The most important factor, yes, Manthan. Any other reason? Okay, so 1 second. Yeah, I'll just give you guys 5 more seconds so that I can drink this. Okay, 5 seconds up. So Manthan has the right answer. It does slow down all the services. If you are firing read queries on a production database, then there's also live queries coming over there. So you're eating into the resource of the rest of the guys who are trying to persist data or even read from that data. So what is the user profile of Gaurav Sen? Well, a read query came in, and then this machine learning bit or the data analyst is also running get me all profiles of users in India. So both of them are contending for the same row. So there might be some concurrency issues. Locks have to be taken. It's slowing down, you know, the production services. So you might want to buy more database hardware. That's a major issue. And on top of that, there was another thing that we had to do this repeatedly. The data analyst would fire the same query again and again without any automatic calculation happening in the background. So they would start having cron jobs actually later on. So yeah, small improvements in the process, but still there was an issue. Okay, the other problem, which is a very interesting problem. I think it only happens, I mean, you only guess it if you have actually worked in one of these companies, is that the data analyst says sales right now is 300. 5 minutes later is 302. So the machine learning code that you ran when the number of sales were 300 gave you a particular output. At 302, it gives you a different output. But when you're at 302, you have no way of getting back the original data. So you made a decision on your data, and there is no auditing. Okay, there is no way to tell that whether this decision was correct or not, because you don't have the data anymore. An update overwrites the data; it's gone forever, and any decision that you have made is actually based on the data, but the data does not exist anymore. Okay, it's as good as going on your on your IDE and on your code, and Git does not have any history. Whatever you do, it just updates it. So you don't even know where the bugs are. Okay, where did the bug get introduced? Stuff like that is very hard. And especially when your behavior is being driven by data, you want some sort of versioning of the data so that you can tell that up till this point, the data was fine. maybe over here somebody corrupted the data by mistake, whatever be the case, we can get rid of this data. Okay, that was one serious problem over here. Let's see if we can get over it later. But even worse is that before we could solve these problems, we had the monolith architecture, which turned into this, a microservice architecture. No longer did you have a single database. You had multiple databases, multiple services, and the request could go anywhere, okay, to any one of these services. Now, the engineers came up with an idea at this point. Basically, large-scale companies came up with the idea that you have a lot of databases, and we do know how to run queries on a single database. Why don't we take all of these smaller databases and combine them into a single one, treat it like a single database, like a view or something. So if you put them together, you get one DB. And the problem is, again, back to a monolith architecture. Okay. And then you can run queries on that. So let's try and make it a single database. How do we do that? You can use something called a data lake. Okay, you're seeing that on the left-hand side, there's multiple streams of data, which is like flowing into this lake. And the lake is pretty big. Okay, there's very little processing done before you push data into the lake. It's almost like you're taking raw data from all the services and pushing it into this data lake. And then on top of the data lake, you will be doing all of your processing, machine learning to get results. And who's bothered about these results? Well, you might have operations teams. For example, if you have a ride-sharing app and someone says that this was a fraud, I was never picked up from my location. Well, maybe through machine learning, you have a decent probability calculation that is the driver saying the truth or the rider saying the truth. Okay. Similarly, there will be alerts. So this is more on the server side metrics, processor usage, memory usage. If it's gone down to 0, probably your code is not working. If it's up to 110%, then maybe you're overheating. So at that point, an SMS should be sent to an engineer, an on-call engineer, that there's something wrong, please look into it. So through machine learning, you can tell if there is any graph, if there's any point in the graph which is an anomaly, which is like shocking, there's a big spike. So that would trigger an alert. And you also have dashboards. So you have product managers, people very senior in the decision-making process, who look at dashboards and say that, all right, I have had sales over here, which is going up day by day. In Asia, we are doing really well. There's something going on in maybe Europe, which is not doing so well. Maybe we can look into that. All those decisions are made based on the analysis that we do on the data lake. Okay, all right, perfect. So there's a few things to consider here. Firstly, we have 5 services upstream. Do we copy the entire database or do we just copy the delta? Okay, and if you say just copy the delta, just copy the difference in the data. So you had 3,000 records at 3 p.m., 4,000 records at 4 p.m. Just send the 1,000 changed records downstream. How do you do that? That's a question. Do you want to timestamp the data? If you timestamp the data, then how about this service is running at a different cron time? Okay, so you run at 3 o'clock and 4 o'clock and 5 o'clock. There's another service which is running at 4:30, 5:30, and 6:30. So there's a mismatch between the times that they're running. That's one thing you can consider. I'm not going to get into detail over here. Do you want to pull data or do you want to push data? So do you want to pull from the services databases up there upstream, or do you want to let gravity work, like you push the data onto the lake? If you're going to push data, then who's going to take the responsibility of pushing it correctly? What if the data is missing in the data lake? Who's responsible? Is it the upstream service? In that case, the upstream service is aware that there's a lake, which might create some issues. Okay, food for thought. Or do you do something like a dual write architecture, where whenever there's a new trip that is being added in the database, you also add it in the data lake at the same time. In which case, your production servers are a little slower because they could have done one thing in 1 millisecond. Now you're going to take 2 milliseconds. And even if you're doing it concurrently, I mean, it's not your problem. Why are you taking that IO port? Okay, so these are some things that you can consider. I'll leave you to it. But let's see what the problem is. The problem is that this data, like I said, is like raw data. It's heterogeneous. There's everybody who stores data as they need it, but when they're dumping it in the lake, that means that there's different varieties of data. There's NoSQL data here, there's graph data here, there's SQL data over there, and even in SQL there might be some having relations, some having denormalized tables. That's a problem. So before we can work with this data, we actually need to clean it, process it. It might have null values, it might have irrelevant columns based on our use case. So how do we do that? We need some sort of processing layer before the lake, and I mean before the end users, which is the dashboards and the alerts and all the other systems, and after the lake. So it needs to pull data from the lake and push it over there. And once we have the processing done, we need to take this clean data and give it to them, right? The downstream services. Okay, so this is the flow. Services, they have databases. Okay, payments has all information relevant to payments. You have the sessions, like when did this user log in, when did they log out. Okay, it may or may not be relevant in some cases. So in that case, in the data lake, you won't be seeing the sessions data at all. You won't be looking at the sessions tables. So different services, driver, customer, so on and so forth, push data onto the lake. The lake does some processing on top of it, which does the clean data. On top of the clean data, you do some machine learning, and then you push out dashboards or alerts or operations. Teams can work on this. Okay. Now, after that is done, I'm talking about this because this is the final result that we need. You can the right word is influence actually, but you can influence the systems that are currently running. For example, you're on Zomato, you ran all this data through the machine learning model, and then finally the results are sent to the ranking algorithm. The results are sent to the allotment algorithm. Like this restaurant is doing really well, bump it up in the rankings. If someone is searching for biryani, this restaurant is doing really well with biryanis, high ratings, send it on top. Okay, and allotment would be something like, which delivery executive do we have nearby to allot for this order? So that depends on the machine learning models that we have. And that's how our system is going to be reacting to changes, continuous changes in ranking and changes in allotment, making it more efficient. Is focus on this white box over here. Everything else is separated out enough. We have services which we understand. There is a bunch of data which is kind of impure in the lake, which we are pulling from these services. And then after the processing, the clean data is basically the machine learning algorithms are going to be running here and influencing all the green boxes. So like I said, the green boxes are the AI bits. The blue box is the machine learning bit. We are going to be focusing on the white box now, which is processing. Okay, and inside that comes this. We have the data lake on the left hand side. This is heterogeneous data. All of that data, first there is a use case. So for example, what you want to do is you want to reduce the number of refunds that you get in your food delivery app. So what you need to do is you need to take data and find those columns where the delivery has been refunded. So if the delivery has been refunded, that is the output which says yes, true value. If it has not been refunded, that's a false value. So that is your output metric. This is what you need to predict given a set of input parameters. How do you train your algorithm? Well, you have all that bunch of other columns in your lake. So for a particular order ID, give me the customer ID, give me the restaurant ID, give me the payment ID, and taking all this data, I will put them all together for a single ID. And then I will basically, after joining this data, I will filter on this data. So let's say I want to find out the behavior of refunds in Mumbai versus the behavior of refunds in New York. And if I get any general things working for me, then I will take that as a general refund characteristic. Okay. So there's a lot of initially when you take the data, there's a lot of filters that you run. So maybe you're not interested in orders which never started. So they have delivery time equal to null. So filter that out. You have, maybe it was a free order. So really you don't care about refunds with free orders. So again, filter that out. So in this way, initially you need to filter the data a lot. So that is your first layer. If you guys know about machine learning, if you guys know about neural networks rather, then you probably have seen that there's this architecture where there's layer on layer of, I think they call it perceptrons. But in this case, they are actually boxes. They are containers which are going to be filtering the data first. The second layer is going to be mapping the data. So you have IP address. What uses IP address in a machine learning algorithm? Not really. So you convert the IP address to a city, to a location, a physical location that you can say, okay, if you are in Mumbai, then your chance of a refund is 3%, something like that. So you take data and you map it into something that we need for our use case. Finally, there might be, this is not necessary, there might be sorting involved. There might be some reduction involved. There might be some expansion involved. Sometimes you take all this data, clump it together and put it in the database as a CSV or something. You might need to break that open. Okay, that might happen here. And then you have your clean data on which you can run machine learning, okay, the right-hand side. So there's data going from the lake, from the filter to mapping, mapping to sorting, sorting to reduction. Let's say reduction is like take the top 10 results, okay, and then you have the nice clean data. Okay, this architecture is called the map reduce architecture. So it's pretty interesting. Yeah, it's not very, let's say, it's not very recent actually. It's been there for a while, but even now it is the underlying architecture of a lot of systems which deal with data, big data. And the best thing about this is that it's so resilient. Have a look at all these boxes that we have. Let's say the red one is box A and the green one is box B. So two computers. I have one on the left, one on the right. They can participate in different parts of the process. So first three-fifths of the data is going to the red box and 2/5 is going to the green box. Okay, but in the mapping stage, there is maybe this box has a GPU. It's really good at mapping. So more of mapping is going on this box than on the red box, and so on and so forth. And so the data flows. It may not flow from one system to another. It might be inside itself, but conceptually it is flowing. In case, let's say the green box crashes, we can hook up a new box and we are good to go. Okay, that's another good thing about this. I was going to talk about fault tolerance, but I think we are a little short on that. So I'll go to the next part. A quick question. I don't know if you guys have this doubt. What happens if we are on this stage? Okay, the green box, it's done a lot of processing. So you see that it went from stage 1 to stage 2, stage 2 to stage 3, stage 3 to stage 4, and it was about to process that data and make it clean data before the green box crashed. If it crashed, did we lose all our data? Right? If a new box is bought in, then the problem is all that work that we did, it could have taken 6 hours, 7 hours. You know, there's a lot of data. It could have taken a long time. After all this work, we lose all of our progress. This doesn't look like a good architecture, right? So does anyone have any ideas around this? How do we save our work that we are doing so that we don't need to retry, especially because these boxes are going to be cheap. So the expectation is that they're going to crash often. Okay, I'll take it out. When we are storing the data in the data lake, is it the exact data that is stored, or is it converted to another form, summarized form in which? Manan, it usually is not summarized because there might be multiple machine learning models which are needed to be run on top of that data. So later on, you know, there is scope for some hindsight. You can take copies of the service data, but ideally you want to persist all the data. Ideally you want to persist it in the raw form and later on do the processing in the lake. Okay, that's the reason why it's a lake. Different streams, no processing being done, no summary, no filtering, just raw data. Okay, Aryan Bhardwaj has the answer. That's correct. Shubham and Vanesh also have variations of the same answer. That's great. So basically, you want to store the previous stage's data. And Aryan has a more accurate answer because you need a database. You can't cache this. Okay, the amount of data is huge. So you will need to store the results also in a database. And the good thing here is that because it's not mission critical, it's not like if this data doesn't reach the other person in the next 3 seconds, then the decision is invalid. No, that's not the case. This runs daily. Takes 6-7 hours. So we can persist it. Then we can tell the yellow box to start reducing it in the next half an hour. Things are fine. Things are working slowly, but you're moving forward step by step. That's the reason why this is called batch processing. You don't do everything together. You do it step by step. Or actually, basically, you take a bunch of records. That's the batch, and then you process it. Okay, and the reason why we are storing it in a database instead of the box itself, instead of the earlier layer saying it, is because if the earlier layer is, let's take an example. Let's say the third layer is sorting, second layer is mapping. The red box crashed. So if the red box crashed, that means that, or the green box crashed. If the green box crashed, that means that all the layers are affected and some data has been lost, which has to be again gone through from the start. So you want the boxes to be stateless. You don't want any data going from the box directly. You want it to be persisted in the database, which gives flexibility to the next layer also. It can start at any time it likes. It doesn't need to be that the moment you get it, you need to start working on it. Otherwise, it will be lost forever. Okay. Okay. Now, once we have that, like these green ticks are basically like you have the data being persisted at every layer. There was a crash. That's okay. Green ticks say that we can just restart from here. The other part, I think we have accidentally hit correct, which is that we want this architecture to be neither push nor pull. We want it to be something like something in between, a hybrid, where we push data, the result onto a database, and we pull from it in the next layer. Okay. Yeah, this is the interesting bit. When you do this, when you have databases on every layer, what happens is you can now decouple the layers themselves. So you have a job scheduler. It runs every half an hour. Every half an hour, it gets up and says, whoever has the data ready, please send it to the next step. So the filter, the 5 boxes in filter, they don't know about who needs this data next. It could be a map layer. It could be a sorting layer. It could be anything. You just need to plug and play in the job scheduler. So all of your logic, all of your business logic is going in the job scheduler, while all of the computations, the raw computations is going onto these boxes. So you have decoupled and made the system more flexible. It's also more scalable, right? You don't need to put the logic into each of the boxes, the code. You just need to tell them what you need to do with this data, and that's it. Persist it. So this is how the data will flow. You send results, not the full data, just the result. Like, yes, I was successful in the computation to the job scheduler. It sends it to the next node, so on. Till you have. We talked about other different implementations for NoSQL and other DBs like graph-based, like Neo4j Tiger Graph. There might be more optimized ones, but no. This is pretty generic. The part that you're talking about is actually limited to the data lake. So if there is a graph database which is on relations and nodes, then you can push that onto this data lake almost like a file. Usually this data lake, by the way, is HDFS, distributed file system, Hadoop, or you have S3, Amazon S3. So they're pretty much like files. You can store any kind of data in these files. And so different types of database data can also be pushed into this. There's a few companies which have change logs, binary change logs, which they push in and then they process that. So those are SQL ones. But yeah, your data source can be anything. So also, I'll give you an example. AWS does provide some sort of functionality in terms of data lake. It has, I think, AWS Data Lake is the name of the thing. So over there, what they do is they do a little bit of the cleaning of the data. They will, I think you can say that if the cost is null, then take the average of all the costs, or take the mean of all the mode of all the costs, or the median of all the costs, and put that as a placeholder. So there are certain functionalities that are readily available. So you don't need to create this lake by yourself. But then large scale companies, they want to have the data just with themselves, usually. How do you define how many nodes at map or sort you will be needing at each layer, and how do we ensure that fault tolerance in a particular layer? Okay, firstly, the number of nodes you need at a map or sort is going to be handled by the job scheduler. Now, if you're talking about how do we load test, like how do you figure out how much time is it going to take? Like you have 1 hour and you want to complete it within 1 hour, which means that you need 50 processors. And if you want to complete in 2 hours, you need 25 processors. How do we do that? Usually it's trial and error, unfortunately. What ends up happening is that you have a person, an engineer, writing a script in the job scheduler saying that this is what I want to run. And during testing, when they're proving the concept, they run it on small data and they note down the times. So when they're running on a production, they actually just extrapolate. That's how it usually works. How do we ensure fault tolerance in a particular layer? Well, let's say sorting goes down. Okay, all the nodes in sorting are down. No problem. Mapping has done its job. Once it has persisted to its database, it tells the job scheduler, I'm done. Now you handle sorting. So the job scheduler will try to assign some containers, assign some nodes. It's not working. That's okay. That's okay. You're not losing any results. So fault tolerance in the sense that you can bring back the nodes without any fear of loss of data. It's immutable. The lake is also immutable, and all the results are immutable in the process. How can we use this when we need faster outputs rankings like trending restaurants? Yes, the changes very quickly. Okay, we'll get to that in a minute. All right, awesome questions, guys. Thanks, Manthan. That is coming up in a minute. Where are the slides? Oh, yes, there they are. So let's try to figure out how this will work when we are trying to reduce refunds in our food delivery system. Initially, we have the data lake. From there, we send data to filter. So we say that if the time is greater than 0, if the delivery time is greater than 0, means there was an attempt to delivery, and the status is a refund, take only that kind of data. Okay, we don't care about any other type of data. Then we say convert IP address to a location in the mapping phase. And you might also say the experience of the delivery executive should be 1, 2, or 3. Because if you take the number of days, minutes, and seconds as the experience of the delivery executive, it's not making much sense, right? Does a kid need a vaccine? If they're less than 5 years, yes. If they're more than 5 years, then let's say no. Okay, so there's a binary 1 or 0. Just like that over here, you're converting continuous input to a discrete output. Okay, and then you have in the joining phase, you might have various things going on. Finally, you have some integrity checks. You just want to make sure that delivery time is not negative or something is not null, or there's one interesting integrity check. For example, the delivery time is 5 a.m. and the order time is 6 a.m. So you ordered after the delivery was made. Okay, that is a integrity check failure, and you ignore that data. Oh, and also another thing is, like, if it is out of operation time, how did it deliver at 5 a.m.? That's not the time when we are running as a business. So you get rid of that kind of data also, probably in the filter stage itself. Yeah. Now, then finally, with this clean data, you find correlations. So what is the chance of a refund if a person is a new delivery executive? 3%. What if they are an experienced delivery executive? 1%. So you see a correlation in experience to output. Okay, similarly, what if the price is very high, or what if the rating is really low? So all that input data, you take correlations, and then you assume causation. So causation is going to be handled by a human being because that requires a lot of brain. Instead, what we do is we have a prediction engine which says that this is the probability of the incoming order becoming a refund. So if it is above 15%, cancel the order, don't accept it, because the cost of refunding the order is going to be more than actually taking the order and making a profit. Okay. So you might suggest an action. The suggested action might be dampen the rankings. For the ranking algorithm, you might just outright cancel the order. You might also increase the fare, whatever be the case, to save your investment. Okay, it's nice. I'll just quickly summarize. In distributed systems, in large-scale distributed systems, data across microservices are stored in a lake. Different sources push it into a lake. It's processed with the MapReduce architecture, which is something that we talked about over here. This is the MapReduce architecture. And then we have some of the engineering challenges, which is correctness, making sure that the data is correct. So there is no data corruption. So we talked about immutability. There is no updates in the data at any point in time. Fault tolerance, like we said, if a processor goes down, if an entire cluster goes down, we are still fine. And performance, at this point, we'll be taking the question of, I think Manan had asked the question. So how do you change rankings in seconds? Okay, or in a finance system where seconds is the metric, this architecture won't work. It will take an entire day. So basically what happens is, instead of this lake, you hook up message queues or event buses onto the services. They all push these events onto the queue, and from the queue you keep consuming events in your machine learning architecture. And the good thing about it is that it gives you real-time insights. The bad thing is that the message queue can't be that large. So you're going to be taking a small window and seeing what are the trends. In this window, the price of biryani has shot up. So maybe you should increase the price of biryani even more to make a bigger profit. Or maybe there is a bug. So it tells you anomalies in real time. It tells you trends in real time. The problem is, I'll just head back to that microservice place. Actually, that will give a better insight. Yeah. From here, all of these services will have queues or event buses, which are going to be sent to the machine learning system directly. Like I said, the problem is that you have a small window in which you're looking into, instead of all of the data that you have generated in the past 1 day or 2 days or 3 days. Okay, that's how you make it real time. Okay, and in fact, getting back to the conclusion, we have taken care of correctness through immutability, fault tolerance by decoupling the architecture, and performance by keeping it. Again, we have taken two solutions. One is a batch processing and one is the stream processing thing. Okay. And finally, guys, if you have any questions, do let me know right now. Okay. Can we use this when we need faster? Yes, Manthan, yes, we can. But we can't use the batch processing. We have to use stream processing then. I know some of you might find this like difficult to follow. So if you need, like I said, there's event buses or databases, and parts of the data are being stored. Some part might crash, stuff like that. So all of this is part of system design. So if you want to have a look, you can go to the YouTube series. It's free. And yeah, that'll give you the basics of how to design systems.
Yeah.
I should have used that as a prerequisite for this talk, but no, I think we're good.
Yeah, I think we're good. So thank you once again, Gaurav, for joining us today. On behalf of the entire Pragma team, I'd like to thank you for taking out some time and joining us. It was an honor hosting you today.
Thank you.